I'm Christopher, and I work for Google on LLVM's runtimes, particularly libc++. And this is the story of how we optimized vector and how it led to some really interesting performance gains and some really terrifying ABI implications. So for a quick recap on vector, it's a dynamically sized array that grows as you add elements. I'm not really going to go into much more detail on that, but what is interesting is what happens when we call pushback, because not everyone may know what's going on there. So let's push back Konnichiwa, and we'll do that one code point at a time. For the sake of this talk, we're going to assume that it's UTF-32, and that will become apparent as to why later on. But we're going to push back each code point one at a time. And we're going to start off with an empty vector. And an empty vector has no memory allocated and no elements in it as a result. So when we go to push back ko, since there's no memory, we first need to allocate some memory on the heap. And so we allocate, because we're putting one thing in, we allocate one unit of memory. In this case, that'll be 4 bytes. And then what we do is we construct the object, so that way it contains the value ko. And then we want to put in the character n. We've run out of capacity here, and so we need to allocate some more memory. So what we do is we allocate a whole new block of memory. We move across the elements that are already in, and then we have an empty spot available, so we can construct the value n. And then when we want to put in ni, we need to allocate a little bit more memory because we've run out of space again. So we now have 4 blocks. Notice that we went 1, 2, 4. We're going to grow by doubling every time. And so then we can construct, and then ni, and then we can also construct chi at the same time, also one after that, without having to allocate anything new. And then when we want to put in the wa particle, we need to allocate a whole new block of memory. And so we now have 8 elements. So we can insert up to 8 elements, and we've only got one thing left to insert, and we are done. So what's the most intuitive way to implement this? Well, if you ask the average person, they typically think that it's going to be implemented using a pointer for tracking the buffer that's on the heap. That's something that is very necessary. Then you need to have an integer to track how many elements are in the buffer, and then this thing called capacity, which tracks how many elements you can actually put into the vector before you need to reallocate. That's pretty much the code representation of what we just talked about. Because vectors use iterators, we also need to think about how we implement the begin and end functions. And so begin just returns the iterator, an iterator wrapping around the pointer to the beginning of the buffer, and end will do exactly the same, but it'll be, instead of at the start of the buffer, it'll be one past the end. So it'll just be data plus size. But this isn't how libc++ implements it. In fact, libc++ does it quite differently. So what libc++ does is it uses pointers to represent everything. And I'll come back to why that is in a moment, but just to go through that a little bit more detail. We start by having the same pointer at the start. That is inescapable. We cannot have memory on the heap and not have a pointer to it. But the next thing that's interesting is that we go to end rather than to size or capacity. And end is a wrapper around end, this end member that's a pointer, rather than interacting with size at all. And then in order to compute size, also to get size, we need to compute it. We do that by doing pointer subtraction. We take the 2 pointers, begin and end, and we just work out what the distance is through pointer arithmetic. And then capacity is done exactly the same way. And graphically represented, this is what it would look like. We have a pointer to the beginning, a pointer to one past the end, which I prefer to refer to as a pointer to where we will insert the next element. And then we also have a pointer to one past the last element that could possibly be in the buffer. Now, I've done a little bit of digging to find out why it is this way, and people in the libc++ space can't really say for certain why it was designed this way when it was, but the consensus is pretty unanimous in that it is probably because C++'s standard library is very iterator-based, and because of that, we want our begin and end to be fast, not our indexing. So if indexing is just as fast, that's great, but iterators are the way the standard library has been designed. But let's actually compare the two implementations and see how things actually fall out. So we're going to take two different cases, the first of which is when the vector's value type has a size that is a power of 2. So, for example, any integer type or a floating point type. If we look at the assembly for x86, we'll see that all we've really done is traded the assembly for size with end when we have the two separate implementations. So the code that was in current implementation of vectors size function now goes to the size-based version's end function and vice versa. Things get a little bit different for the ARM code generation though. We can see that it is slightly cheaper to have a size-based vector as opposed to having a pointer-based vector. And I'll come back to that when we take a look at the next case. But for now, just keep in mind that having a call to the size-based end is slightly better than the pointer-based size function, even though they're both doing some amount of pointer arithmetic. The other case that we want to consider is when that value type size is not a power of 2. And the larger a type gets, the less likely it is to have to be a power of 2. But one particular case that stands out is a vector of vectors, because whether it's something that's size-based or something that's pointer-based, if your size type and your pointer type are going to be 8 bytes each, then that means that your vector is going to be a total of 24 bytes. That's not a power of 2. So that is an interesting case to consider. And if we look at the assembly, it is quite different indeed. The size and the end for the pointer-based vector and the size for the size-based vector are equivalent. Those aren't interesting, but it's the other two that are interesting. If we look at those, we can see that size-based end is substantially smaller and does less complex operations than the pointer-based vector's size. And the reason for this is because pointer arithmetic isn't equivalent to integer arithmetic. Integer arithmetic is very trivial, and pointer arithmetic doesn't just do a subtraction, it also needs to divide by the value type size, because otherwise we're just getting two random points in memory, not working out what the distance between those two random points in memory is. And so we end up getting down to a point where we end up with a large magic number, and then having to do some other things that we can't optimize out any further. Whereas with the size-based vector implementation, we are able to optimize it down to what it is. And I've really talked about ARM at the moment, but if we look at the x86 code, it is also somewhat simpler for the non-power of 2 case. This becomes much, much more important when we turn on hardening mode. And a hardened libc++ looks something like this. It's basically adding a set of checks to operations that might otherwise be unsafe, so that way they cause crashes. So in this particular case, the subscript operator will make a call to size to find out what the whether or not we are in bounds. For the first case, that's fine because the vector's got one element in it. But if we make a call and try and get something beyond one, then we end up crashing the program. Problem is that this is going to unconditionally call size, and that's going to end up with a fair amount of performance overhead, particularly at scale. Kiniko mentioned earlier that turning on hardening can result in some very noticeable amounts of performance loss. So this matters a lot. And what we're going to see some interesting results with size-based vector and how this addresses that problem quite a fair bit, because we've looked at some things and worked out that the vast majority of our calls, so of our hardening checks, are actually done in vector, and that relates to checking the size of vector. So a lot of this requires benchmarking. We can't rely on micro benchmarks. Those are very unreliable. They require a very specific setup and are very finicky, and they aren't representative of what a real program looks like. What we want, at the very least, are macro benchmarks on load tests. A load test puts something under strain. It simulates what we might expect in the real world, and if it's designed correctly, then we can run a macro benchmark on top of that, and then we'll be able to work out what the results might look like. And for us, for some of our servers, it looked like we were going to get a 0.2 to a 0.5% increase in queries per second. And for some of our most important servers, we were able to predict that we were going to see a fairly modest but still noticeable decrease in operational costs. And even though it's modest, it is something that is statistically significant, and that is still worth keeping in mind. These are all predictions. We probably want to see what some real results are for talking about this as a potential thing to include in upstream libc++. And so it turns out that yes, our results ended up being really good. We ended up getting the amount of time we spend in vector size down from 0.6% to 0.04%. Vector end didn't change at all in terms of its time spent, which means that optimizing on size is not going to negatively impact someone that uses iterators. And overall, we think that there might be somewhere between 0.15 and 2% decrease in the total amount of time we spend in vector. Now, I promised you a horror story. So this is a tale of Hyrams Law. Can I get a show of hands who's familiar with Hyrams Law? Handful of hands? Cool. Okay. So basically, Hyrams Law is an observation that was made by a former colleague of mine. It's basically saying that once you reach a sufficient number of users, your API, whatever your API is touchable by the user, will end up becoming the API itself, no matter what your documentation says. Doesn't matter if you have a giant sign saying, please don't use this, it will break at some point. Someone's going to depend on it. If you want to go to hyramslaw.com, that will take you to a little bit more of an explanation, and you'll also be able to see the corresponding XKCD comic, because yes, there's an XKCD comic. So let's take a look at some code that is not terribly far from reality. It is representing a vector that has been type erased to support any number of dynamically sized arrays in the wild that this particular library depended on. And so the salient parts here are that the vector is actually contained in a pointer to void, and it has some flags, and then it needs to extract those things, and then it will work out what to insert based on a reinterpret cast to a vector of bytes. And it will just reinterpret it as a vector in this particular way. Graphically represented, the current implementation, this was fine because even though it was undefined in C++, because everything is based on pointers, pointers remain stable. And so when we want to reallocate memory, we will just end up subtracting 2 pointers, get the size and the capacity, and be able to go on our way because we have the correct answer, because we can be computing it on the fly. So everything's destroyed. But when we are using a size-based vector, those pointers have to be computed. And that means that when we do our reinterpret cast, it's no longer going to look like this. It will instead look like this. And that means that our vector, when we attempt to destroy it, still has some memory life lying around, because we said that the capacity was going to be slightly smaller than what it should have been. Now, fortunately, we have tools that are able to capture this. This is a address sanitizer on that's caught this, but there are other things like tcmalloc that are also capable of catching this problem. So this only happened once in a while, but it happened quite a few times internally. So we had to clean those up as well. And the fix for this particular code base was simply to rely on virtual functions and to have the correct type represented using a series of templates. We're in the process of upstreaming this, so there's an RFC on Discord, and we have a pull request for the first half of this work. It is split in 2, with the other half to be submitted once we've got the feedback on the first half, because the 2 pull requests will look very similar. So to recap, vector is historically represented using a trio of pointers, but tracking the size and capacity as integers is a way to significantly improve performance. This change breaks the ABI, and Hyrams Law is always waiting to catch you. Thank you so much for listening, and I'll field any questions now, if there's time.
Yeah, thank you for a great talk. I wonder how you decided to attack size method of vector. Did you get this from profiling, that this is something that can be optimized, or I don't know, intuition, gut feeling? What?
So if I understand the question, you're asking like, how do we know to even look for this?
Yes. How you decided to attack this method in the first place?
I see. So we ended up looking at the assembly, and it was like looking at the code and then looking at the assembly and determining from that we were able to potentially improve it. And then it was a lot of experimenting to confirm that was the case. Does that answer the question, or have I left something?
Well, not quite. Why you decided that this piece of assembly is important? Because you started with the original idea is that STD is based on iterators, so
yep.
Size is supposed to be not important.
So size is unconditionally being called when you do subscript operations, and if we look at code, we see that we're doing a lot of subscripts. So we wanted to make sure that was not being an unconditional size that couldn't be improved.
Any other questions?
That was a pretty cool talk. Thank you. When you showed the performance numbers, were those on top of x86 or ARM?
That I can't disclose.
Sorry if I missed it, but the performance numbers, were they for hardened libc++ or not?
They were for hardened libc++, yes.
Right. Okay. So is it fair to say that it doesn't matter as much for non-hardened libc++?
It still matters. You get a lot more performance, a lot larger of a performance gain with hardening enabled.
All right, thank you.
Thank you for the great talk. I'm sorry if I missed something, but is the size-based approach is applied only if the size of the value type is a power of 2, or applied to every type?
So if I understand the question correctly, you're asking, does this only matter if the type size is a power of 2?
Yes.
Okay, so it matters in both cases, but it matters a lot more when the size is not a power of 2. And on top of that, it only, so when the size is a power of 2, there isn't going to be as much of a difference when you're using x86.
So you applied this, whatever the type size it is.
Right, yes.
Okay, thank you.
Any?
So if you change the ABI of studio vector, have you ever considered optimizing it with other techniques like embedding the first few entries into the studio vector? I think it's doable if you can break the ABI. Right?
Sorry, could you please repeat that? I didn't catch everything.
So, well, breaking the ABI is a chance to optimize with other techniques like allocating a few more and allocating a few entries and embed it into the vector itself as instead of
Oh, you mean like a small buffer optimization? Right.
Something like that, and you can do that.
Okay, thank you for repeating that. Unfortunately, the vector specification doesn't allow us to do that particular optimization. It needs to be movable, I think, in constant time, and there's one other requirement that I'm forgetting that also prevents us from being able to implement it that way. But to answer your question about more generally, libc++ has this thing called an unstable ABI, where when you build libc++, you turn on a flag and it makes a bunch of optimizations that will break the ABI, but you'll be able to have a faster libc++ as a result. And so the answer is both yes and no. We need to make sure that it works, that the code is maintainable from both a stable ABI perspective and an unstable ABI perspective. But provided we can do that, then adding another optimization, say in 6 months' time, is probably not going to be an issue if it has substantial performance gains.
Any other questions?
Was the fact that the IR does not have a pointer sub operator a contributing factor in the performance results, or did you not look at that?
Sorry, I didn't catch the start of that question.
So the IR doesn't have a pointer sub operator, so you have to have into pointer, which stores your ELSing information. Was that a contributing factor in your performance improvements?
That I don't know. I'm less familiar with the back-end details. Sorry.
Probably yes, because you don't know it's an exact subtraction. So my question is connected to the previous talk. So in the previous hardened libc++ talk, it mentioned there was like a 0.3% penalty for performance. Is that with this optimization turned on or not?
That would have been, Kineko, can you confirm this? But I think that was without the optimization? Without? Okay.
Yeah. Right, thanks.
Thank you, Kineko.
All right. Thank you so much, Christopher.